Okay, so the first thing we're going to talk about in this section are conditional propositions. And if you don't want to think about this word conditional propositions all this time, these are the same thing in English as if-then statements. And here's a kind of typical example that you might see or say. If you make an A on all of your exams, then you will pass discrete math. But since we're talking about logic, we need to be a bit more concrete in our definition. I can't just say this is the English phrase and then we go from there, because we need to eventually talk about truth tables. So what we'll do next in the definition is here. If P and Q are propositions, then the proposition if P, then Q. So I'm kind of translating my English into more logical kinds of things. This proposition is called a conditional proposition. And we're going to get a little bit new notation. Instead of writing out the English all the time, usually what we'll do is write this. So P, and then an arrow pointing to the right towards Q. So if you ever see this symbol, it means if P, then Q. And a little bit more information. The first part of the if-then statement, P, is usually called the hypothesis. The if part. And the second part, Q, is usually called the conclusion. And this kind of matches up with our understanding of regular English language. An if kind of statement is a hypothesis. If this is true, then maybe that. And then the conclusion is the other part. Okay, so the next thing to do is to consider the truth value of the proposition, because we want to make a truth table for this guy. And let's go back to the example from before, the first one, the one that said, if you make an A on your exam or all your exams, then you will pass discrete math. And remember, we're considering if P, then Q. So what I want to consider first, because this is the easier one to think about, is what happens if P is true. So what happens if you actually make an A on all of your exams?
Then you'll pass the class, right?
Right. So if P is true, then you definitely will pass the class, right? So Q, the other half of the statement, must be true. Because we know if you make an A on all of your exams and then somehow you fail the class, something went really wrong. That shouldn't be possible, right? So you must pass in order for this conditional to be true. So I don't think anyone will disagree with me there. But let's go to the one that's a little bit harder to think about. So what should happen if P is false?
Then would
So,
Q be false?
okay, so let's think about that. I'm going to write this first. So P is false means you don't make an A. Okay, and then your answer was Q should be false. So that means you don't pass. And definitely that could happen, right? If you don't make an A on all of your exams, maybe you did really badly, so badly that you can't pass the class. So that's definitely possible. But what would happen, say you made an A on 2 exams and on the 3rd exam you made a B? What do you think would happen in that case?
You could still pass the class.
Right. So you didn't make an A on all of your exams, but you still did pretty well, I think, if you made 2 A's and a B. I mean, that's really good. So actually, you could still pass. So I'll make a note here. Maybe you made 1 B. Or maybe even all B's or all C's. You could still pass. So if P is false, then Q could be either true or false, and the original statement, if you make an A on all of your exams, then you will pass discrete math. This statement is perfectly fine. It's still true, even if the first part, you make an A on all of your exams, if that didn't happen. So does that make sense? Are there any questions over that? Okay, so maybe everyone's happy with that. Let me leave that there for just a second. Looks like someone might still be writing. Okay, let's go ahead and move on. Okay, so we needed to think that through, an example like that, because the next thing we want to do is fill in this truth table for our conditional statement. So there's 4 possibilities for the simple propositions P and Q. And now we have to just fill in what we were just talking about. Because we know if P is true, if you'd made that an A on all of your exams, then Q must also be true. So the first row is true, where you pass the class. And the second row, where you fail the class, is false. And we also talked about if you didn't make an A on all of your exams, maybe you made a few B's or even a few C's, but you still passed the class, so Q is true. And that's perfectly fine. Your statement is still fine. And it could also be that you failed all of the exams, or maybe you did really bad on a couple exams, and then you failed the class. And that's also fine. Your conditional statement is still perfectly fine. So this is still true. So the conditional, if P then Q, is actually only false in this one case, where the hypothesis is true, but the conclusion is false. Every other time, we get a true.
So how is both false and but comes out true?
So think back to the example. Remember, if you make an A on all of your exams, then you'll pass discrete math. So let's think about what would the two falses be. So if this is false, that means you didn't make an A on at least one of your exams. So maybe you could imagine you got Fs on both of the exams, if this is not true. And you know, if you fail all of your exams, then you're probably going to fail the class, right? So even though this part is false and you failed, so this passing is false, the overall statement, the conditional statement, is still perfectly fine. It's still true that if you make an A on all of your exams, you'll pass discrete math, even if it happens to be that you failed because you didn't do it well in your exams. This conditional is still perfectly true. And I understand that this is a little bit hard to grasp, at least at first. So make sure you just keep this in your mind, that if the hypothesis is false, so if the left part of your conditional is false, then it doesn't matter what the conclusion is. And there's actually a word for this. If the conclusion, sorry, if the hypothesis is false, these two rows, then these truths are what we call vacuously true, because they don't actually tell you anything. They're simply true because the hypothesis was false. For example, here's a perfectly true conditional statement. If pigs can fly, then 2 plus 2 is equal to 5. This is a true statement. But it's vacuously true because, well, pigs can't fly. It doesn't actually say anything because pigs can't fly. And that's where this word comes in, vacuously. Okay, any other questions before we try an example? Okay, so let's try this one. We have three simple propositions, P, Q, and R. On the left side of my conditional, I have P or Q, and on the right side, I have the negation of R. So the way that you would read this in English is if P or Q, then not R. Maybe I can write that down over here as a translation, because it's always important to keep in mind what your mathematical symbols actually mean in English. now for the truth table, I've already put in the 3 simple propositions, and now I want to do something like the homework exercise that we did before the lecture started. We want to take the component pieces of our statement and build it up into the more complex one. So for this one, I have 2 pieces, P or Q. And this one, not R. And then those 2 pieces are put together to make the overall conditional statement, P or Q, then not R. Now that we have our columns settled, we've picked our columns, we can start filling in, starting on the left with the simple things and then working to the right to get to the more complex propositions. With 3 simple propositions, we're going to have 8 possible combinations of truth values. So let me fill these in really quick. True, 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 false, true, false, true, false, true, true. And then we could have true, false, 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 true, false, 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 true, and then finally 3 falses. Like this. Okay, so now we work to the right, so we need to look at this column, P or Q. In order to fill this in, we're going to totally ignore the value of R. So you can imagine covering it up, and you can literally cover it up with something because it doesn't matter right now. What needs to happen for P or Q to be true? Someone tell me.
At least one of them needs to be true.
Good. So there's actually only 2 rows where we're going to get a false. Which 2 rows?
The bottom 2.
The bottom 2, right, where both of these are false. So we have falses down here. And for all of the other rows, there's at least 1 true in these 2 columns. So go ahead and fill those in. Like so. And that's finished. We move to the right, and we look at the negation of R. So for this, we'll actually now ignore this column. I'll wait a second though, in case some of you are still writing. We'll ignore this column and these 2 columns to fill in this one. So all we do is switch the truth values that we find here. So true becomes false, false becomes true. Like this. Okay. One more column to go. Here's our final conditional statement. For this column, we care about the truth value of P or Q, the left side, and the truth value of not R, the right side. So we actually only care about these 2 columns now. We can totally ignore this. When is the conditional statement false? It's when the left side was true and the right side is false. So everything else is going to be true, except like this first row where the left, the hypothesis is true, but the conclusion, not are, is false.
Professor,
So-
can you read that? Like the statement on the top right, can you
This
say
one?
it, I guess? Yeah.
Yeah, I wrote it out here. This is how you would say it in English. If P or Q, then not R.
Thank you.
You're welcome. So this is only going to be false if the hypothesis is true, but the conclusion is false. So that's something like this first row. That's a false. Then we'll get a true. And then we have two falses, actually. And everything else is going to be a true statement. Okay, any questions?
Why are the last two true?
So these correspond to the bottom rows of this truth table, right? So think back to where you maybe failed one of your exams or you made a B on one of your exams. So you could either pass or fail your class if you didn't do well on your exams, but the overall conditional is still true. And
I got you. So the hypothesis fails, so we assume true.
right, so if the hypothesis is false, then it doesn't matter what the conclusion is. It's going to be true no matter what.
All right, just checking.
Yeah, that's a good question. This is definitely not straightforward. Okay, so something to keep in mind is that in English, there are actually many ways to say conditional statements that are equivalent, that the same thing as an if-then statement, like this one. A proposition like, I will cook pasta for dinner only if there's a clean pot is actually the same as this. If I cook pasta for dinner, then there's a clean pot. And it might not be totally obvious why that's the same, so let me clear it up by writing the opposite. So if I switch the order, because it looks like the if switched positions, if I switch the order of the sentence, then it would look like this. If there's a clean pot, then I will cook pasta. So the meaning of these two sentences is actually quite different. The first one says, if I cook pasta for dinner, then there's a clean pot. So what this means is that, well, you're being lazy. You don't want to do any dishes before you even cook. So you're only going to clean if there is already a clean pot. And that's exactly what this is. Because the only time this sentence is false is if you cook pasta, but there was no clean pot. If the hypothesis is true, but the conclusion is false. So this is the same as that. But this one's a little bit different when you switch the order. If there's a clean pot, then I will cook pasta. This is more, well, it feels a bit more certain, right? You're definitely going to cook pasta if there's a clean pot. That's different. So there are lots of phrases like this in English. Like if you put an only if instead of an if then, that are the same as conditional statements. And there are a few more examples in your book. So I would definitely encourage you to read through those examples of different phrases that you can use for if-then statements. Any questions over that idea? Okay, so next we need to talk about this. So here I'm switching the order. Q is pointing at P and P is pointing at Q. And this has a special name in logic. If P and Q are propositions, then the proposition if P, then, excuse me, let me start that over again. If Q and P are propositions, then the proposition if Q, then P is called the converse of if P, then Q. So converse means you're switching the order or direction. And just as a silly little example, here's something that you could say. If it's raining, then it's cloudy. I think we can all agree on that statement. If there's rain falling, then surely there must be a cloud over you. But if I switch the order, we might not agree with it. If it's cloudy, then it's raining. So does the second one seem true? Does this is this a good proposition? Can you think of a time when it's been cloudy but it wasn't raining?
Yeah, I can think of a few times of it just being cloudy.
Right, exactly. So if you change the order of your conditional statement, if you look at the converse, it actually has a different meaning than the original statement. So make sure you keep that in mind. The order of your conditional statements matters. Any questions? No? Okay. So we're done, at least for a little bit, talking about conditional statements. The next thing we're going to talk about are if and only if statements. Here's the definition. If P and Q are propositions, then the proposition P, if and only if Q, is called a biconditional proposition. When you write it this way, it's similar to the conditional. So you have an arrow pointing at Q, but the arrow also points the other direction. So both left and right. And this double arrow gets to the name, the biconditional. So it's somehow two conditional statements. And if we have time today, or maybe next time, we'll talk a little bit more about what I mean by two conditional statements. So the biconditional statement is true when P and Q have the same truth value. Okay, so if you're worried about your connection, like this message that I just got, I am recording the lecture, so if you miss something, you'll be able to go back and look at it later. So back to this. The biconditional is true when your two propositions have the same truth value. So the biconditional is something like an equal sign. So it's true when they're equal to each other in some sense. So it's a good comparison to have in mind. And I can just fill in the truth table now. We need our 4 rows. And our biconditional. And we get trues when they're both true or when they're both false, because they have the same truth value. Oops. And then when they're different in the middle 2 rows, we'll get a false for the biconditional. And to fill in a quick example using math, because you run across these kinds of ideas really often in math, could be something like this inequality that says x is less than 2x minus 3 if and only if 3 is less than x. So if you want to run through the algebra really quick, all I've done changing this to get that is I moved the x's to the right. So I subtracted x and then I added 3. So these two inequalities are the same. It's just that this one has been solved for x. So let's think real quick about why this should be true even if we have 2 falses. So what I want to do is to plug in a number. And we can pick anything that'll make this false. So maybe I'll plug in 0. 0 is a convenient number. What would you get on the left if you plug in 0?
You would get
Go ahead.
0 is less than 0 minus 3, which is not true.
Right. So you get 0 is less than minus 3. We know that's false. Good. And I'll fill in the rest of the statement. If and only if. And then you can just put a 0 over here. This is also false. So my biconditional statement, my original one, is still true. 0 is less than minus 3 if and only if 3 is less than 0, but they're both false. So I'm not really claiming that 0 is less than minus 3. I'm just saying that this is true if and only if this other thing is true, even if both of them are false. Normally, when we see inequalities or expressions like this, we only care about when they're true. But when we're doing logic, we have to care about what happens when they're both false. It's just a little bit tricky to think about it sometimes. Any questions over the definition here? Okay, so the main reason why we're going to talk about biconditional statements is this definition here at the bottom of the page. And let's just go through it, and then I'll see if you have any questions. Suppose capital P and capital Q are propositions made up of simple propositions that I'm calling P1, P2, up through Pn. And then I say that P and Q are equivalent or logically equivalent written P and then almost an equal sign, except I have 3 horizontal dashes. If P and Q have the same truth value for any values of P1, P2, up through Pn. So another way to say this is that P, capital P, if and only if capital Q, oops, don't need that, if this is always true, because they always have the same truth value. So I think something that can be confusing about this definition is what I mean by this first sentence when I say these propositions are made up, simple propositions. So what I mean is that P could look something like this. So capital P has, well, capital P is more complicated because it's made up of simple propositions. It's actually maybe a conditional statement. And Q could be something else, like this one. Okay, any questions over this idea before we do an example?
I'm still writing this down.
Okay, yeah, I can wait a second. And just let me know when you're finished.
Okay, I'm finished.
Okay. So our example here is known as De Morgan's laws. And these are the two laws. They say that not P or Q is equivalent to not P and not Q. And the second one says that not P and Q is logically equivalent to not P or not Q. So the basic idea here is that the negation, the not symbol, gets distributed into the parentheses, but the symbol in the middle gets flipped. So the or becomes an and the and becomes an or. And if you remember from the first section when we were talking about sets, there was also a property that I called De Morgan's property. And it looked a lot like this one, except in that property, well, we were dealing with sets. And instead of ands and ors, we had intersections and unions, and then knots were complements. But the idea was the same. The complement distributed and the symbol switched. So unions became intersections, intersections became unions. And that's why these two ideas get the same name, because they look the same. So what I want to do in this example is to actually show that this is true. So this left side is actually logically equivalent to the right side. And the second part, showing that number 2 is true, is actually a homework problem. So I'll leave that one for you. Okay, so we start building our truth table, and I already started mine. So we have two simple propositions, P and Q, and then we need to build up these other propositions from the simple ones. So I looked inside of the parentheses, and we have a P or Q, so I'll make that my first column. And then on the right half, we have a couple building blocks. We have the negation of P, so we'll give that a column, and then the negation of Q. That should get its own column as well. And then you'll want to finish by giving the whole left side a column. So not P or Q. And then you'll give the whole right-hand side its own column. And I'm checking to see if these two propositions are logically equivalent. That means these two columns here, standing in for my left and right sides, these two should have the same truth values. because no matter what I plug in for P and Q, these two need to have the same truth values if they're logically equivalent. So let's just work through and check that that actually works. We have 4 rows in this problem, since we're starting with 2 simple propositions. And then we build up P or Q. We need at least one true. That means we'll have a true, 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 and then the last row where there are 2 falses, we'll get a false for P or Q. And now we'll forget about this column for a minute and fill in the column for the negation of P. That means we have to look at the first column and switch the truth values. So true becomes false, and false becomes true. Then we move on to the negation of Q. So for the moment, we only care about this column, and we're going to switch the truth values that we find here. So my true in the first row becomes false, and all the falses become true. We keep on working. Now we have the negation of P or Q. That means we need to look at this column for P or Q and switch the truth values. So we get 2 falses, or actually 3 falses, excuse me, and then a true in the bottom row. There we go. And now to fill in my final column for not P and not Q, we'll look at these 2 columns for those 2 negations. And in order for the AND statement to be true, both sides have to be true. And we only find a true for not P and not Q at the same time in the bottom row here. This one will be a true, and the other 3, when we're looking at these truth values, we'll get falses. Okay. So now that we've completed the truth value, are our 2 statements logically equivalent? Are these 2 columns the same?
Yes.
Right. So we have false, 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 and true. And that's how you check for logical equivalence. So you'll make a truth table. Excuse me. You'll make a truth table for each side. Well, you need a column for each side in your truth table, and then you have to see if your columns are the same. So this is the basic idea that you'll be doing on your homework from this section. Let's see. So we have 3 minutes left in class. This is a pretty good stopping point. Do you guys have any questions?
Can I briefly see the first page of notes?
The first page of notes? Sure. Was there a particular part of it?
Yeah, it's the proposition of P is called the.
Ah, okay. So that's hypothesis and conclusion.
Thank you.
You're welcome.
All right, Dr. Connor, I'm going to head out, but thank you for the lesson.
Okay, good to have you. See you next time. And if
Thank
there
you.
aren't any other questions, then you guys can go ahead and leave. And
Have a good week, Professor. See you Wednesday.
thank you. See you
Well-
Wednesday.
Can I see what's under that?